One way to think about radioactivity is that they are just spontaneous nuclear reactions. Okay, all of them have a positive Q value because they're releasing energy to become more stable. Okay, now if you look at this zone of stability here, and we think there could be an island out here of relative stability. It's just how do you get to it, right? These are all the nuclei. This is how many neutrons there are, right? So this would be A minus Z, right? And then this is the proton number, which is Z, right? Okay, A being the total number of nucleons, right? So if you look at this graph, these things are just too big, okay, to be stable. And so they're going to move kind of this way by emitting alpha particles, right? So an alpha particle, alpha decay is that you release, a 4-2, a giant piece of stuff to just reduce the sheer number of nucleons, right? On this side, we've got things that are neutron rich. So things that are on this side are neutron rich, right? And so they will undergo beta minus decay. Now, if you recall, a beta minus, right, is just a neutron. Basically, one of the neutrons turns to a proton plus an electron. A beta minus, an electron, and a cathode ray are all the same thing. They're just electrons. Okay, and remember, we also have an anti-electron neutrino. Okay, and the anti-electron neutrino carries away some of the energy, so we really can't say a whole lot about how much energy this thing has, right? Okay, so neutron-rich things get rid of their neutrons by moving this way, right? Okay, on this side, we've got things that are proton-rich, right? And then the proton decay that takes care of that is that we go proton turns to neutron plus positron, right? Right? And then a regular matter electron neutrino. So this has a -1 lepton number, +1, etc. Right? Okay, and that's your beta plus, right? The other thing it can happen too is that it can capture an electron, an orbital electron. Okay, and there's one of the problems on the little packet that we have that's going to cover that, right? And then the final thing is that the nucleus can give off, and it's I'm going to say it's always, okay, I could be wrong. It's always subsequent to one of these decays, right? An alpha decay occurs. Sometime later, a gamma ray is given off. Remember, that's just a photon, okay? It has no charge. It has no rest mass. It's just a little packet of pure electromagnetic energy that's fired off. And it's fired off unpredictably at some unpredictable time after either an alpha decay, beta minus, or a beta plus decay, or electron capture could also cause that. Okay, so that's the concept there. These are just nuclear reactions. You do them the same way you do binding energy and Q value as far as the energy goes. And just keep in mind that alpha energies are actual, like this thing actually has all that energy. But in the case of beta minus and beta plus, that neutrino carries away an unpredictable amount of energy. Now, the total energy is the same as you can figure out the Q value of it, right? But we can't say that the beta particle or the beta plus has that, okay? I think that's all I need to say about that radioactivity. So, all right.